Here we have a solution that is basic. And the reason it's basic is because of a hydrolysis equilibrium involving the anion, in this case cyanide. So, what we can do is we can start by writing the equilibrium that is involved here. So what happens is cyanide, and since we say this is a hydrolysis reaction, that means that the cyanide ion is reacting with water, and that's in equilibrium with the conjugate acid of cyanide, which is hydrocyanic acid, or HCN, and hydroxide ion. Now we can write a Kb for this equilibrium. The Kb expression always looks something like this. The concentration of the conjugate acid times the concentration of hydroxide ion divided by the concentration of the conjugate base. So the question becomes now, how do we calculate this Kb from the information that's given? What we can do from the pH is calculate the POH, and then from the POH we can calculate the hydroxide ion concentration. To calculate the POH, we take the pH and we subtract the pH from 14, which is pKw. And that gives us 2.59. Next, we can calculate the hydroxide ion concentration simply by raising 10 to the negative 2.59 power. If we do this, we get 2.6 times 10 to the negative 3 molar. Now, because the hydrogen cyanide is generated from the same reaction as the hydroxide ion, and it's a one-to-one reaction, the concentration of the HCN is going to be the same as that of the hydroxide ion. So in this case, that would also be 2.6 times 10 to the negative third molar. The concentration of the cyanide ion is going to be the initial concentration of the solvent solution, since the cyanide was generated from the dissociation of potassium cyanide in the first place, minus the amount of cyanide ion that underwent hydrolysis. So in this case that would be 0.10 molar minus the 2.6 times 10 to the negative third molar. Now, what you're going to find is if you do this and then round the molarity back to the appropriate number of significant figures, it's not going to change. We still get 0.10 molar. Again, it's worth doing this calculation though, because that won't always be the case for calculations like this. Many times it will be, but not always. So now we can go ahead and calculate our Kb because we have the concentrations of all the different components of this equilibrium involved in the Kb expression. Our Kb is going to be 2.6 times 10 to the negative third squared, since both those concentrations are the same on the top or in the numerator, divided by the concentration of the HCN, which we just calculated to be 0.10 molar. If we plug that into our calculators, we get 6.8 times 10 to the negative fifth.